In the previous videos, we saw a power series that was convergent for all real numbers x. We saw an example of a power series that was convergent on an interval of the form -2 to 2, where it was closed at -2 and open at 2. But you see, this interval is centered at 0. It goes 2 units to the left of 0 and 2 units to the right of 0. And the same thing happened actually with the geometric series, right? It is convergent for x's in the interval -1 to 1. Again, it's centered at 0. 1 unit to the left of 0, 1 unit to the right of 0. Then, is this always going to be the case? Are these just the only possibilities, or is there anything else? Well, the next theorem is telling us precisely that the set of values for which a power series is convergent is an interval centered at 0 with a little twist. So it could be an interval that goes from -r to r, where r is some real number, and it could be open, it could be closed, it could be just open at the left and close at the right, or close at the left and open to the right. But we can also think of the whole real line as an interval centered at 0, just an infinitely long interval. And then also the point 0, we can think as a collapsed interval when like this r is equal to 0. So those are the only possibilities for the sets of points x for which a power series is convergent. And we have even more. We know that this power series is absolutely convergent for all the points x that are in the open interval -r to r. This is very nice because if you remember, absolutely convergent series are the best. They're very nicely behaved and we can treat them pretty much just like finite sums. So in this case, the power series will behave just like a polynomial. The interval on which the series converges is called the interval of convergence, and this r is called the radius of convergence. And here we're allowing r to be 0 or infinity. Together, when r is equal to 0, we get just this point 0, and when r is infinity, we get the whole real line. Perfect. So here there is a picture of what this theorem is telling us. You see, if we start centered at 0, if we go r units to the left, r units to the right, then my series converges absolutely in this pink region that I have. If we are x is bigger than r or less than -r, then my series diverges. But when x is -r or r, I have no idea what's going on. My theorem doesn't tell me what happens there. If you remember, that's what happened in the example in the previous video. When we got to those endpoints, in that case was x equals 2 and x equals -2, we didn't know what to do with the ratio test. We had to do something different. This is precisely these two r and -r points where the theorem is not telling me what's happening. So let's take a look at the proof of this. We're first going to show that if my power series converges for some x naught different from 0, then the power series actually converges for an interval. And then from there, we're going to build our entire proof. So we're going to assume first that my series of an times x naught to the n converges for some x naught that is different from 0. Now, because this series converges, then the terms of the series, the sequence of the terms of the series converges to 0. So in particular, this sequence is bounded. So there exists an m such that the absolute value of an times x naught to the n is less than or equal to m for all n. Good. Then, well, if I have an x whose absolute value is less than the absolute value of x naught, then I'm going to do the following. I'm going to look at the absolute value of an times x to the n, and I'm going to rewrite it by just multiplying and dividing by the absolute value of x naught to the n. Haven't done anything, it's just that. But look at this. Now, the part on the left, the absolute value of an times x naught to the n, I can bound by m because of what I just said. And then the absolute value of x over x naught is less than 1 because I know that the absolute value of x is less than the absolute value of x naught. So I'm going to call the absolute value of x over x naught r, and I know that r is just strictly less than 1. So then what happens is that I can bound this quantity by m times r to the n, where r is, as I said, the absolute value of x over x naught, and this is less than 1. So here you see, now I have the terms of a sequence here, which is the absolute value of an times x to the n, is bounded above by the terms of a geometric series with r less than 1. So I will use the basic comparison test here to compare the series of the absolute value of the an times x to the n with that convergent geometric series. So then that tells me that the series of an times x to the n is absolutely convergent. Therefore, I know that if a power series converges for some x naught, then it converges absolutely for all those values of x whose absolute value is less than the absolute value of x naught. And that is going to be quite helpful. Now, how do we proceed? We're going to define R to be the supremum of this set. So the set of the absolute value of x such that the series an x to the n converges. So what I'm doing here is I take an x, I check if the power series converges for the value of x. If the answer is yes, I take the absolute value of it and I put it into my set. And I'll do that for all values of x in the real numbers. We're going to see later that this r is precisely the radius of convergence. So here, the first thing to note is that this set is not empty. And the reason why this set is not empty is, well, we know that the power series always converges at least for x equals 0. So we know that 0 is always in the set. If my set is also bounded, then the supremum exists and is a finite number. If it's not bounded, well, r, we could think of r as being infinite, right? The supremum would be an infinite number. Okay, that is cheating a bit, but we're going to say that if my set here is not bounded, the supremum is in positive infinity. Okay, so now if r is equal to 0, the supremum is equal to 0, that means that my power series was only convergent for x equals to 0. If now my set is bounded and I get that r is just a number, a positive number, I'm going to suppose that I have the absolute value of x strictly less than r. Then there exists an x naught such that the absolute value of x naught is strictly bigger than the absolute value of x, such that my series of an times x naught to the n converges. Because you see, if not, then the absolute value of x would be an upper bound of my set. But remember that r is the supremum, r is the smallest upper bound, and the absolute value of x is strictly less than r. So the absolute value of x cannot be an upper bound. Therefore, there has to be some value x naught such that this absolute value is bigger than the absolute value of x, and that my power series converges for x naught. Okay, so now that we have this, then by our previous argument, then I know that the series of an times x to the n converges absolutely. Therefore, then I know that my power series of an times xn converges absolutely for every x such that the absolute value of x is strictly less than r, because we picked an arbitrary x. The only thing that we were asking for it was that the absolute value of x was strictly less than r, and for that value of x we showed that my power series was absolutely convergent. So we know that as long as the absolute value of x is less than r, my power series is absolutely convergent. And now what happens if the absolute value of x is greater than r? Well, this series has to be divergent, because if not, then r wouldn't be an upper bound, right? So if we have an absolute value of x is greater than r and my series is convergent, well, then that would be an element of the set that is bigger than r, so that would be a problem. So that is why if the absolute value of x is greater than r, then the series diverges. And then we have the last case. So if r is infinity, so if my set is unbounded above. So I said I'm cheating a little bit by saying r equals infinity. It's kind of an r equals infinity. Well, then the series would have to be convergent for all values of x. And that completes the proof.